Chapter 1.4 Economic and Social Challenges. From an economic perspective, there are a number of limitations inherent in aquaponics systems that make specific commercial designs more or less viable. Goddek et al. 2015, Vermeulen and Kamstra 2013. One of the key issues is that standalone independent hydroponics and aquaculture systems are more productive than traditional one-loop aquaponics systems, Graeber and Young 2009, as they do not require trade-offs between the fish and plant components. Traditional, classic single-loop aquaponics requires a compromise between the fish and plant components when attempting to optimize water quality and nutrient levels that inherently differ from the two parts. For example, desired pH ranges and nutrient requirements and concentrations. In traditional aquaponic systems, savings in fertilizer requirements for plants do not make up for the harvest shortfalls caused by suboptimal conditions in the respective subsystems. Delayed et al. 2016. Optimizing growth conditions for both plants, Delayed et al. 2016, Goddek and Vermeulen 2018, and fish is the biggest challenge to profitability, and current results indicate that this can be better achieved in multi-loop decoupled aquaponic systems because they are based on independent recirculating loops that involve 1. Fish, 2. Plants, and 3. Bioreactors, anaerobic or aerobic, for sludge digestion and a unidirectional nutrient flow, which can improve macro and micronutrient recovery and bioavailability, as well as optimization of water consumption. Goddek and Kiesman, 2018. Current studies show that this type of system allows for the maintenance of specific microorganism populations within each component for better disease management, and they are more economically efficient in so much as the systems not only reduce waste outflow, but also reutilize otherwise unusable sludge, converting it to valuable outputs, for example biogas and fertilizer. Independent recirculating aquaculture systems and hydroponic units also have a wide range of operational challenges that are discussed in detail in chapters 3 and 4. Increasingly, technological advances have allowed for higher productivity ratios, see figure 1.2, which can be defined as a fraction of the system's outputs, for example fish and plants, over the system's inputs, for example fish feed and or additional fertilization, energy input for lighting, heating, and pumping CO2 dosing, and biocontrols. Figure 1.2 shows an aquaponics system seen as a black box scheme. We do not get to see inside the box, but we know the inputs and the outputs, for example fish and plants, and the waste. When considering the many challenges that aquaponics encounters, production problems can be broadly broken down into 3 specific themes. 1. System productivity, 2. Effective value chains, and 3. Efficient supply chain management. System productivity. Agricultural productivity is measured as the ratio of agricultural outputs to agricultural inputs. Traditional small-scale aquaponic systems were designed primarily to address environmental considerations such as water discharge, water inputs, and nutrient recycling, but the focus in recent years has increasingly shifted towards economic feasibility in order to increase productivity for large-scale farming applications. However, this will require the productivity of aquaponic systems to be able to compete economically with independent, state-of-the-art hydroponics and aquaculture systems. If the concept of aquaponics is to be successfully applied at a large scale, the reuse of nutrients and energy must be optimized, but end markets must also be considered. Effective value chains. The value chains, added value, of agricultural products mainly arise from the processing of the produce such as the harvested vegetables, fruits, and fish. For example, the selling price for pesto can be more than 10 times higher than that of the tomatoes, basil, olive oil, and pine nuts. In addition, most processed food products have a longer shelf life, thus reducing spoilage. Evidently, fresh produce is important because nutritional values are mostly higher than those in processed foods. However, producing fresh and high-quality produce is a real challenge and therefore a luxury in many regions of the world. Losses of nutrients during storage of fruit and vegetables are substantial if they are not canned or frozen quickly. Barrett 2007, Rickman et al. 2007. Therefore, for large-scale systems, food processing should at least be considered to balance out any fluctuations between supply and demand and reduced food waste. With respect to food waste reduction, vegetables that do not meet fresh produce standards but are still of marketable quality should be processed in order to reduce post-harvest losses. Although such criteria apply to all agricultural and fisheries products, value adding can substantially increase the profitability of the aquaponics farm, especially if products can reach niche markets. Efficient supply chain management. In countries with well-developed transportation and refrigeration networks, fruit and vegetables can be imported from all around the world to meet consumer demands for fresh produce. But as mentioned previously, high quality and fresh produce is a scarce commodity in many parts of the world, and the long-distance movement of goods, supply chain management, to meet high-end consumer demand is often criticized and justifiably so. Most urban dwellers around the world rely on the transport of foods over long distances to meet daily needs. Grewal and Grewal, 2012. One of the major criticisms is thus the reliance on fossil fuels required to transport produce over large distances. Barrett, 2007. The issue of food miles directs focus on the distance that food is transported from the time of production to purchase by the end consumer. Mundler and Kreiner, 2016. However, in terms of CO2 emissions per ton per kilometer, 1 food mile for rail transportation, 13.9 grams CO2 per ton per kilometer, is not equal to 1 food mile of truck/road transportation, as truck transportation has more than 15 times greater environmental impact. McKinnon, 2007. Therefore, transportation distance is not necessarily the only consideration, as the ecological footprint of vegetables grown on farms in rural areas is potentially less than the inputs required to grow food in greenhouses closer to urban centers. Food miles are thus only a part of the picture. Food is transported long distances, but the greenhouse gas emissions associated with food production are dominated by the production phase, specifically the impact of energy for heating, cooling, and lighting. Engelhop, 2008, Weber and Matthews, 2008. For example, Carlson, 1997, showed that tomatoes imported from Spain to Sweden in winter have a much lower carbon footprint than those locally grown in Sweden, since energy inputs to greenhouses in Sweden far outweigh the carbon footprint of transportation from Spain. When sourcing food, the transport of goods is not the only factor to take into consideration, as the freshness of products determines their nutritive value, taste, and general appeal to consumers. By growing fresh food locally, many scholars agree that urban farming could help secure the supply of high-quality produce for urban populations of the future, whilst also reducing food miles. Bon et al., 2010, Dos Santos, 2016, Hui, 2011. Both areas will be discussed in more detail in section 1.5. From a consumer perspective, urban aquaponics thus has advantages because of its environmental benefits due to short supply chains, and since it meets consumer preferences for high-quality, locally produced fresh food. Milisic et al., 2017. However, despite these advantages, there are a number of socio-economic concerns. The major issue involves urban property prices, as land is expensive and often considered too valuable for food production. Thus, purchasing urban land most likely makes it impossible to achieve a feasible expected return of investment. However, in shrinking cities where populations are decreasing, unused space could be used for agricultural purpose. Bonch and Latin, 2005, Schilling and Logan, 2008, as is the case in Detroit in the United States. Mock et al., 2010. Additionally, there is a major issue of urban planning controls, where in many cities, urban land is not designated for agricultural food production, and aquaponics is seen to be a part of agriculture. Thus, in some cities, aquaponics farming is not allowed. The time is ripe to engage with urban planners who need to be convinced of the benefits of urban farms, which are highly productive and produce fresh, healthy, local food in the midst of urban and suburban development.